Around 90% of all life on Earth was wiped out once, and the cause was not an asteroid. It was a volcano, but not the kind you are picturing, and not Yellowstone. Yellowstone gets the headlines, but it is not the largest threat this planet can produce, and it never has been. There is a kind of eruption so much bigger that comparing the two barely makes sense, and it has been behind nearly every mass extinction in the history of life. By the end of this, you will know exactly what it is, why it keeps happening, and why it suddenly matters right now. Yellowstone is not the thing that should scare you, and the headlines have had it backward for years. Every few years, the same story comes back around. Yellowstone is a supervolcano. Yellowstone could erupt and end civilization. Pyroclastic flows, ash across the planet, a global winter, the end of the world. The story is recycled because it works, not because anything new has happened. And tonight I want to do something different with it. I want to tell you what is actually true about Yellowstone, which is bad enough on its own, and then I want to show you the thing that is genuinely far worse, a kind of event most people have never heard a single word about, even though it has been behind nearly every mass extinction in the history of life on Earth. Here is the part the clickbait never tells you. Yellowstone, as enormous as it is not the largest volcanic threat this planet can produce. It is not even close. And even a full Yellowstone eruption, the worst-case version, would be a continental catastrophe, not an extinction. It would devastate North America. It would not end the world. The thing that ends worlds is something else, something bigger. And the strangest part of this entire story is that this bigger thing is the reason Yellowstone exists in the first place. So let me take you up the ladder, one step at a time, until you can see the real monster clearly. Because once you understand what is actually capable of wiping out most of life on this planet, you will also understand why it matters right now, today, in a way that has nothing to do with a national park in Wyoming. The best way to understand the scale here is to climb. And the first rung is one you already know. On the 18th of May, 1980, Mount St. Helens erupted in Washington state. It was the largest volcanic eruption in the recorded history of the lower 48 states, and the collapse of its north flank became the largest landslide ever recorded anywhere on Earth. For most Americans, that is the mental image of a volcanic disaster. Hold on to it, because on the ladder we are about to climb, Mount St. Helens is the smallest rung. It is the unit we are going to keep multiplying. Take one step up. The eruption of Mount Pinatubo in the Philippines in 1991 was roughly 10 times larger than Mount St. Helens, and it did something Mount St. Helens never could. It threw a cloud of sulfur high into the stratosphere, above the weather, where it spread into a haze around the entire planet and reflected a fraction of the sun's light back into space. The result was that the whole Earth cooled by as much as 1 degree Fahrenheit for a period afterward. One volcano, one eruption, a measurable drop in the temperature of the entire world. That is the first time on this ladder we see the real weapon, and it is not the lava or the blast. It is the ability of a large enough eruption to reach into the atmosphere and change the global climate. Take another step up. The eruption of Mount Tambora in Indonesia in 1815 was about 10 times larger than Pinatubo. It threw so much material into the sky that the following year became known across the northern hemisphere as the year without a summer. Frost killed crops in June. Harvests failed across Europe and North America. People starved thousands of miles from the volcano because of what a single eruption did to the sky. And notice the lessons stacking up at each rung. A farmer in New England in 1816 had no idea a mountain in Indonesia had stolen his summer, because the damage did not come from the blast or the lava. It came from the climate, carried around the world through the air. Each step up this ladder, the explosion matters less, and the atmosphere matters more. And that trend does not reverse as we keep climbing. It accelerates. Now take the final step. Multiply Tambora by 10, and you reach Yellowstone, which means a major Yellowstone eruption is on the order of 1,000 times the size of Mount St. Helens. That is the scale the headlines are pointing at, and they are right that it is staggering. Yellowstone has done this 3 times in the recent geological past. About 2.1 million years ago, about 1.3 million years ago, and about 631,000 years ago, when it carved out the basin we now call the Yellowstone caldera. If Yellowstone erupted like that again, The devastation would be real, and it would be enormous. The collapsing ash column would generate pyroclastic flows that scour the surrounding landscape clean of life. Modeled ashfall shows a dense inner zone burying the region under more than 1,000 millimeters of pulverized rock, with serious effects reaching well beyond Missoula, into Canada, and down into Colorado and Utah. And volcanic ash is not soft. It is shattered rock. It does not biodegrade. And it does not wash away on any timescale that matters to us. Ash over the agricultural heartland would threaten the food supply far beyond the blast zone. So I am not going to tell you Yellowstone is harmless. I am going to tell you something more useful, which is that even all of that is not enough to end the world, and the people who watch this system know it. Yellowstone will not sneak up on anyone, and that is the first reason not to lose sleep over it. A system that large cannot move toward a major eruption quietly. Before it ever erupted, there would be huge swarms of earthquakes. The ground would swell upward by many feet, and the geysers, the heat output, and the gases escaping from the ground would all change in ways the monitoring network is built to catch. Right now, none of that is happening. The system is quiet. But the deeper reason not to fear Yellowstone is the one that opens the door to the real story. Even a full Yellowstone eruption is too brief and too limited in total volume to cause a global mass extinction. It throws out hundreds of cubic kilometers of material in a short burst, and then, on the scale of the planet, it is over. To kill 90% of life on Earth, you need something that does not stop after a few years. You need something that keeps loading the atmosphere for a very long time. And that thing exists. It is called a Large Igneous Province, and that dull name is part of the reason almost no one talks about it. To understand what it is, you have to understand that the inside of the Earth is not a solid, still ball of rock. It circulates, slowly, like a pot of water heated from below. Hot rock deep in the planet rises because it is less dense, cooler rock sinks, and this churning is one of the main engines that moves the continents. Sometimes a column of that hot rock, called a mantle plume, rises all the way from deep in the mantle, possibly from the boundary with the core thousands of kilometers down. As it rises, the pressure on it drops, and that drop causes it to melt in enormous volume. When that happens, you get eruptions on a scale that makes a supervolcano look small. A single large igneous province eruption can pour out up to 10,000 cubic kilometers of lava, and it does it again and again over the life of the event, flooding the landscape and stacking up layers of dark basalt that end up kilometers thick. This is the jump that matters. A supervolcano like Yellowstone is measured in hundreds of cubic kilometers. A large igneous province is measured in millions. That is the difference between a national catastrophe and a planetary reset. And these events are not science fiction, and they are not confined to other planets. The most recent one happened in the United States, and you can go stand on the evidence this weekend. The Columbia River flood basalts are the most recent large igneous province on Earth, and they began about 17 million years ago across what is now eastern Washington, eastern Oregon, and western Idaho. The word flood is literal. Lava poured out of long cracks in the ground in such volume that individual flows traveled all the way across those states and ran into the Pacific Ocean. If you have ever driven through the Columbia River Gorge and looked up at those dark, layered cliffs, you have already seen it. Those cliffs are stacked lava flows, layer on layer, each band a separate eruption, and at their deepest, the Columbia River basalts are more than 4 kilometers thick. Picture what that region was while it was happening. The land, for as far as you could see, was a moving sheet of molten rock, advancing across the country, filling valleys, and the air was thick with volcanic gas. It happened in pulse after pulse, separated by quiet centuries, for a very long stretch of time, and try to hold the volume in your head, because it is the kind of number that slides right off the brain. A single one of these eruptions could put out enough lava to bury a small country many meters deep, and the Columbia River event was not one eruption, it was a long series of them stacked into a pile 4 kilometers thick at its deepest. The most peaceful scenery in the Pacific Northwest, the orchards and the river gorges, sits on top of the frozen record of one of the most violent things this planet can do. People drive through it every day and call it a scenic route, with no idea they are looking at the cooled body of a monster. And here is the detail that ties this ancient flood of stone directly to the volcano in the headlines. The Columbia River flood basalts are not a separate story from Yellowstone. They are the same story at its beginning. Yellowstone is the dying remnant of that flood basalt event. And once you see how the whole thing clicks into place, the mantle plume that drives Yellowstone sits more or less in one fixed spot, deep below the surface. But the crust on top of it does not sit still. The North American plate is sliding slowly southwest, dragging the surface across that stationary plume like a sheet of paper pulled over a candle flame. The flame burns through at one spot, then the paper moves on, and the burn mark migrates. Over millions of years, that leaves a track. You can see the exact same mechanism in the Hawaiian Islands, where one active volcanic island sits over a fixed hotspot and a chain of older, dead islands trails away from it in the order they were burned. Yellowstone is doing the same thing on a continent. The youngest activity sits under the park today. And if you follow the track to the southwest, across the long, smooth scar of southern Idaho called the Snake River Plain, you find a line of older and older volcanic centers leading straight back toward the region of the Columbia River flood basalts. The plume flooded the Northwest 17 million years ago, and ever since, the continent has slid over it, carrying the surface expression of that hotspot east until it arrived under Wyoming, where it sits now, steaming as Yellowstone. So the headlines have it exactly backward. The frightening thing is not that Yellowstone might become a planet killer. The frightening thing is that Yellowstone is what a planet killer looks like after it has mostly burned out. That forces an obvious question. If this is the faded version, what does the fire look like at full strength? The Columbia River event, as enormous as it was, is one of the smaller members of this family. The true giants are larger still. The largest large igneous provinces in the record are almost beyond imagining, and their names are about to matter. There is the Deccan Traps in India, which was erupting right around the time the dinosaurs died. There is the North Atlantic Igneous Province, born as Greenland and Europe tore apart. And there is the Siberian Traps in Russia, tied to the single worst catastrophe in the history of complex life. Each of these involved the emplacement of millions of cubic kilometers of magma in a geologically short window. And these events are not one-time freaks. They recur roughly every 10 to 30 million years, and the machinery that produces them is still running under our feet right now. For a long time, science had no good explanation for the great mass extinctions in the fossil record, and largely ignored them. That changed in 1980, when researchers found evidence of an asteroid impact at the exact moment the dinosaurs went extinct, about 66 million years ago. That discovery made mass extinction a serious scientific question, and it led people to ask whether something inside the Earth could also drive extinctions. They looked at the large igneous provinces, and they noticed the timing seemed to match. Over the next 3 decades, as the dating of both the eruptions and the extinctions grew more precise, that match did not fall apart. It got tighter. Of the roughly 14 or 15 recognized mass extinctions over the last 600 million years, almost every single one lines up with a large igneous province. What makes that match so convincing is that it survived scrutiny. When researchers first noticed the dates seemed to overlap, it was a shaky hunch, because the numbers on both sides were fuzzy. The real work was 3 decades of painstaking radiometric dating, measuring the decay of radioactive elements locked in the rock to pin down exactly when each eruption and each extinction happened. And as the dates got sharper, the connection did not weaken. It strengthened. That is the kind of result scientists start to treat as cause rather than coincidence. The asteroid that killed the dinosaurs is the famous one. It is also the exception. The repeat offender, the thing that keeps showing up at the scene of the worst die-offs in Earth's history, came from inside the planet, from the same churning interior whose faded ember sits under Yellowstone today. A flood of lava in one region cannot kill life in an ocean on the far side of the world, so the global killing has to be done by something that travels everywhere. And it is. It is carbon. These eruptions release a tremendous volume of carbon dioxide, enough to warm the entire planet significantly and push it into a hothouse climate that lasts millions of years. But the warmth itself is not what kills. The killer is the speed. The onset of these events is abrupt. There is a sharp initial pulse of carbon and a sharp jump in temperature, and that rapid change slams the environment into a new state faster than living things can adapt. The same eruption also acidifies the oceans and drains them of oxygen, creating dead zones. It is not one weapon, it is many, all radiating out from a single rate of carbon that life cannot absorb in time. And the reason the speed matters so much is simple. Life is remarkably good at adapting to almost any conditions, hotter, colder, more acidic, if it has enough generations to adjust. Evolution is a real and powerful response, but it runs on the clock of generations and cannot be rushed. Pour the same total carbon into the air over 10 million years and life keeps pace and may even flourish. Pour it out over a few thousand years and you overrun that clock, and whatever cannot adapt fast enough simply dies. It is the same carbon either way. The only thing that changes is the speed. The clearest proof of how lethal this is comes from about 252 million years ago, an event so severe it is called the Great Dying. The Siberian traps erupted, and around 90% of all species on Earth were wiped out. Life came closer to ending completely then than at any other moment we know of. And the reason Siberia was so uniquely deadly should make you sit up, given where this is going. The magma there rose through ground packed with coal and petroleum, ancient buried carbon, and it cooked those deposits and released them into the sky, on top of the carbon already pouring out of the magma. The worst extinction in the history of life was, in part, a fossil fuel event. The planet dug up its own buried carbon and burned it. And the thing that turned that carbon into a mass grave was not the volume alone, it was how fast it arrived. That brings us to the part of this story that is not about the deep past at all. About 56 million years ago, the Earth ran a smaller, cleaner version of the same experiment, an event scientists study as the closest natural analog to modern climate change. Global temperatures spiked by roughly 4 to 6 degrees Celsius, almost certainly driven by a rapid injection of carbon tied to a large igneous province. It was not a full mass extinction, it was survivable, but it was dramatic enough and well enough preserved in the rock that researchers use it to understand exactly what rapid carbon does to a living planet. And it gives us one number that recontextualizes this entire story. During that ancient warming, the carbon that drove a 4 to 6 degree temperature spike was released at a measurable rate. Scientists have worked out how fast it came, and the rate of carbon release back then was still something like 4 to 10 times slower than the rate human activity is releasing carbon today. Read that again. We did not match the ancient catastrophe. By the one variable that turns a survivable warming into a mass extinction, the speed, we have already exceeded it. Using furnaces and engines instead of mantle plumes and lava, the deep past is not warning us about a danger that might someday arrive. It is holding up a mirror, and the reflection is already moving faster than the event scientists study as a model of catastrophe. So here is where this lands, and what to actually watch. The giant volcanic eruptions, the large igneous provinces, will happen again. That is certain. But they are not a threat to you, or your children, or your civilization, because the next one is almost certainly millions of years away, and a new plume rising would announce itself long in advance. The version of this threat that is not millions of years away is the carbon, and the difference is everything. Every species that died in every mass extinction was a passenger that never saw it coming and could do nothing about it. We are the first to read the mechanism out of the rock while the carbon is still rising, which means the rate is not fixed the way a mantle plume is. It is the sum of human choices, and human choices can change. The most dangerous force in the history of this planet was never the fire or the ash. It was the speed at which carbon enters the air. For the first time, that speed is in our hands. And that is both the most alarming fact in geology and the only hopeful one. What happens next is not written in the rock. It is still being decided.